Thank you very much for coming. We've got Henry Burton from Artelligen, who's going to be giving us 25 minutes on what they've been doing in the insurance space, and also giving us a background of what machine learning actually is. And also Jason Cabral from Zenith, who will be talking about his experience with actually using machine learning as well. So thanks very much, Henry and Jason, and everyone enjoys it.
Thanks, Sebastian. Okay. Well, good morning. As Sebastian said, this morning we're going to be talking about machine learning. And I've heard recently that machine learning has been likened a little bit to teenage sex. Everybody's talking about it, but no one really knows what they mean. And so what we're going to do this morning is take about 25 minutes to demystify machine learning, explain to you what it is, and then, as Sebastian will hand over to Jason, who's going to talk about actually implementing machine learning in his own organisation. So here's what we're going to cover in our 25 minutes, and that'll be myself and my colleague Sandy. First of all, a bit of a quick overview of us. What is machine learning? Why are we doing it now? We're going to look at how you can use machine learning in risk selection and pricing, underwriting. We're going to look at some other use cases for machine learning in insurance, and then briefly how to get started. So a quick overview on who we are. We're Artelligen. We were founded in last year, 2016, and we are focused on the application of machine learning to insurance problems. And we're very focused on insurance because we are insurance people. So I spent 10 years in the Lloyd's and London market breaking commercial and specialty risk, and my colleague Sandeep here is a 12-year qualified actuary, but also, and very rare, a machine learning expert. So two worlds collide. And we have a third colleague who's not in the States this morning, who's a financial modeler, risk analyst, and transaction structurer. So, what is machine learning? It's a subfield of artificial intelligence. And that's an important point, and I will come on to how it sits within the AI family in a moment. It blends techniques and principles from computer science, applied statistics, and software engineering. It enables computers to make accurate predictions by detecting complex patterns in data. And then it generates code itself, which enables those patterns then to be recognized in new data. And so really, whatever form of machine learning we're talking about, whatever type of problem we're trying to solve, or tool set that we're using, those principles will always apply. And we will hopefully colour this a little bit in a moment. So let's put machine learning then into this context of AI, because people use these terms AI, machine learning, interchangeably, and actually what you can see there is that machine learning is a subset of artificial intelligence. And then within that, within the field of machine learning, we have a subset of machine learning called deep learning, and we can talk about that again in a little bit later. And actually the line between deep learning and machine learning is fairly blurred. It's more a matter of complexity and the type of tool set that you're using rather than anything else. And I suppose at the heart of this, we're talking about machines that learn. Okay? They improve over time as they are exposed to new data. Here are some applications of machine learning, again, just to put some context around this. These are the various different sort of sub-branches of machine learning, if you like. At the top there, we've got what you might call predictive analytics, and that's what we're really going to focus on this morning. Then you've got natural language processing, speech to text, text to speech, expert systems, using machine learning to plan and optimize strategies, robotics, obviously, very much the sort of the heart of robotics, and computer vision. All of those things, machine learning, all of those things apply to the definition we started with: data, recognizing patterns, training, learning as exposed to new data. Just to confuse you a little bit further, so all of those applications all apply to the same thing. We can break machine learning down into three areas: supervised, unsupervised, and reinforcement learning. Supervised learning, unsupervised learning, reinforcement learning. Supervised learning is what we're going to be focusing on today. And that is very much a task-driven thing. In other words, you start with some data, and you start with a task. I want you to predict this, or I want you to classify that. Unsupervised machine learning is data-driven. You start with a big piece of data, you give it to the model, and you say, I want you to tell me to group things as you see fit. Identify clusters. So that can be very useful in, say, understanding your market better. So you might say, well, here's all the people under 25, and here's all the people who live in Swindon, and here's all the people. Actually, you could use a clustering system to tell you, identify groupings that you would never have thought of. And then lastly, we have reinforcement learning. This is where you have your driverless car, or indeed the machine learning tools that won, or model that won the game of Go, if you recall, if you had it last year or so. That's reinforcement. It's trial and error, finding a way, and being told each time whether that's right or wrong, and then when it finds the right way, off it goes. So those are the three things. But we're going to focus on supervised learning, and in particular, regression. And in other words, predicting something using data, as opposed to classification, which I'll show you right now. So here's an example of supervised machine learning with a classification problem. Very simple, and you may wonder why you want to do this, but we can train a model to tell us whether the machine is looking at a picture of a cat or a picture of a dog. Now, there would be some computer vision in this. What we would do is feed the machine lots and lots of pictures of cats, lots and lots of pictures of dogs, and we would convert those pictures into mathematical values. In computer vision, you break that down into pixels. Each pixel would have a red, green, blue value against it. So that's what the machine would be understanding. It doesn't know what a dog is, it doesn't know what a cat is. But if you show it enough pictures of different dogs, and you show it enough pictures of different cats, you should then be able to say, when you show them a new picture, tell me whether this is a cat or a dog. And as you show it more and more pictures, and correct it where necessary, it will get better at recognizing cats and dogs, because they each have unique features, right? And features in common. So how would that apply in an insurance context? A classification task, you could have two claims, claim A, claim B. Tell me which of those claims is genuine and which of them is fraudulent. So in exactly the same way, we would take lots and lots of claims that we knew to be genuine and lots of claims that we knew to be fraudulent, and we trained the system to recognize those so that when we presented them with a new one, it could say, I think that's a fraudulent claim. So, why now? Because actually, machine learning algorithms were developed in the 1950s. But the world is changing fast. Firstly, the availability and the cost of computer processing power is revolutionizing our ability to crunch data. And in particular, cloud computing. So now you don't need to scale up your IT infrastructure internally in order to use massive computing power. You can go out to the likes of Amazon and others in order to rent that space as and when you need it. So this is changing the face of machine learning massively. Second thing is the abundance of data. Never before have we had so much data with which to crunch and use in machine learning. And not just any old data, increasingly we have enormous volumes of real-time and continuous data emerging from sensors and telematics of all kinds. And I don't just mean in cars and smartphones, but I mean everywhere within the business, within the commercial world, within engineering. Platforms have sensors and all of it generating enormous amounts of data. The other thing that's very important is that the ever-growing libraries of machine learning tools, these are the algorithms that power these models, they are all open source, freely available right now for anybody to go and get. What matters is how you put them together. That's where you get the value from. But they're all freely available. And there's some examples of some of the libraries that exist of these machine learning tools. But the important thing I want to make, point I want to make is on the why now. The data that contained on the internet right now is estimated to be about 5 million terabytes. Okay? And of that, Google, amazingly, has indexed only 200 terabytes, or 0.04%. So we are just think about existing data. We are using almost none of that existing data currently to inform our understanding of the world around us. And indeed, within organisations, something like a similar percentage of data is utilised. Think of all the information and data that's contained within an insurance company or broker. Almost none of it is being used in any sense. Certainly not from an analytics perspective. But what's changing is the sum of human knowledge. And they said back in, until about 1900, the sum of human knowledge doubled every century, roughly. From 1945, it doubled every 25 years. Now it's doubling every 13 months. And IBM estimate that with the Internet of Things, very soon, human knowledge will double every 12 hours. And what do we mean by human knowledge? We mean our understanding of the world around us. So the Internet of Things, those sensors producing all of this data, will allow us to understand and model the world around us in ways that we couldn't possibly imagine right now. So what are the implications for the insurance industry then with all of this? Well, it will, I think, fundamentally allow us to move away from a predictive modelling environment where we seek to ask what might happen, and we have many, many highly sophisticated and well-established tools and models to help us do that. For example, we want to be able to predict how the frequency and severity of claims in order to generate a premium. But we should be able to move into a world of preventive modelling, where we don't just say what is going to happen and what could happen, but also how can we influence that? What are the things that we need to be able to do in order to prevent those claims or manage our risk internally, so that the market can move towards dynamic risk management, real-time exposure modelling, real-time exposure management. So, I'm going to hand over to my colleague Sandeep, who's going to talk about some machine learning myths.
Thanks, Andy. Okay, so you've heard what machine learning is, and you've probably also heard or read in the media about a lot of myths around machine learning. And before I start on what some of the myths are, it seems to me that if you just read newspapers or blog articles, it's very much hyped up that areas like driverless cars, drones, robotics, these are probably the only areas where machine learning can make a huge impact. That's not necessarily true, and some of the myths, I'm going to try to cover that. But before I start off, machine learning is a set of tools, or rather I should say algorithms, designed by computer scientists, statisticians, and other people, that can be applied to any problem if you can specify the problem well enough. It doesn't have to be driverless cars or drones. They are the sort of things that catch the media attention and public attention more. Some of these myths some of these algorithms are very complex to understand. One of the myths are, well, they're too opaque. Yes, compared to the traditional models that people generally use, statistical models, they seem very opaque. But I would say, and there's a lot of debate around this, if you delve into it really deep enough, if you spend enough time on it, you can really understand how the algorithm is coming up with a prediction. The prediction might seem bizarre, might seem super accurate in the presence of other existing models, but it's possible to find out. It's not as easy as a traditional statistical model, but it's possible to find out how the machine is arriving at a certain very accurate prediction. So they are opaque, relatively, not totally opaque. It's not a black box, as some media or the press around it is. Again, this is another myth, is like, if there's pre-existing human knowledge, so I give you some data, and here's a machine learning algorithm. You blindly turn the handle and apply that algorithm, and you expect a fantastic answer. Well, it might come up with a fantastic answer, but it's also possible to tell the machine, well, I've been in this field for 20 years, 10 years, whatever. I have some pre-existing knowledge, pre-existing experience about these sort of claim events or this sort of line of business. It is possible to inform the machine even before it starts predicting that, can you incorporate this knowledge before you even start going on building all those complex algorithms. So it's not like it's just database. It's also, if you have experience or some inside knowledge about a line of business or a particular problem, it is possible to put that in mathematical terms before you run the machine learning algorithm. Another myth is this. So I would not say it's not a silver bullet. It's not like you can solve any problem just by throwing data at a machine using a machine learning algorithm. So if you put garbage in, you'll get garbage out. And that does not necessarily mean the data is bad. It can also mean if the data is uninformative, then no machine learning algorithm can help you. Like a very common example used in statistics classes is if you're trying to predict the intelligence of students, and if you collect data on their shoe sizes, you probably know that shoe size probably has very little correlation with the intelligence of a person. Now, if you put a machine learning algorithm in there, maybe the data is perfect, but what you're actually feeding in is uninformative data. Then it will probably give you an answer, but it will give you a false sense of security. So it might be a very accurate prediction, but do not always think that garbage data necessarily means the data quality is bad. The data there has to be some information content in the data to the problem you're trying to predict, and only then machine learning can help you a lot. Another thing is like, well, all machine learning models are fantastic, they're not biased at all. That's not true. The practitioner who's actually implementing machine learning, they have to be careful while they're implementing the machine learning pipeline about a lot of biases that might creep in. Again, I'll give you an example, and this is again a very simple example. This is from the computer vision community. So about 10, 12 years ago, there was this some mini project organized by DARPA, which is the American security agency. So they tasked a couple of computer vision researchers, can you design a machine learning algorithm that can distinguish between American tanks and non-American tanks? So these researchers came up with a fantastic algorithm, and when they actually went to DARPA, and DARPA fed new images of tanks, American, non-American, it was a complete disaster. So later these researchers, and these were top-class researchers in their field, they came back and then they analyzed, and what they found out was, when they trained the model, the training set of American tanks, the pictures of American tanks were all shot in broad daylight, while the pictures of non-American tanks were shot on cloudy days. So what the machine actually learned was to distinguish between cloudy and sunny days. It did not really was distinguishing American and non-American tanks. So remember, machine learning models can give you fantastic results, but you do not think they're unbiased. They can be led astray. So you really need to know what you're doing. So that therein what the expertise comes in. So what I'm trying to say in the last, within the paragraph, they are fitting the noise, not actually what you're trying to predict. It's ignoring the signals. You have to be very careful. And this is a real life incident. Again, a common myth is, well, as Henry said, well, if you have tons and tons of data, only then will machine learning work. And for example, big data. That is not necessarily true. So what I'm trying to say here is, like for like, if you pump in the same data set using a classical, statistical, or traditional methods, and side by side you apply machine learning appropriately on the same data set, it's very, very likely that machine learning will outperform the classical methods by a large extent, if not significantly, but they will perform. And that does not have to be big data. You do not have to have terabytes or gigabytes of data. So even on small data sets, if you use the right tools of machine learning, if you use them appropriately, and if the data set has information content in it, machine learning algorithms will outperform traditional algorithms in almost all contexts. And by the way, statistical traditional methods are a very special case of machine learning, so that the huge round circles that Henry showed, so statistical models form a very small corner of that big space of machine learning models. The final comment is, the myth is, well, only big companies with huge, massive budgets can actually implement this. That is not true. A large part of the reason for that is the software, the algorithms. Most of them, even though they're cutting edge, they're all freely available. You can download them off the internet. If you know what you're doing, they're all free to use. All you probably have to pay for is the resources, the hardware resources. If you're buying resources, cloud computing resources of Microsoft, Amazon, you pay for the hardware resources. If you buy a server, then you pay for the server. You're not necessarily paying for the algorithms. So the algorithms are free, and also the hardware costs, the computer processing power, they are all increasing, but the cost is not really increasing that much. So you do not necessarily need a big budget, and this is not necessarily true for large corporates with huge amounts of now I'm going to talk about a little bit about some of the advantages, talk about some of the myths. So the following two slides are a bit text heavy. It gets a bit technical. So one of the tools that a lot of actuaries use in personal lines is generalized linear models called GLMs. And by definition, GLMs are generalized linear models. So they assume a linear relationship between the predictors or the data variables and the thing which you're wanting to predict. What machine learning does is it removes that linearity assumption. So you can fit highly non-linear data sets. Now you can assume, even if I give you, say for example, you think shoe size is predictive of intelligence. Just assume for the time being. Now what linearity does is, linearity tries to say, well, intelligence is some multiple of shoe size. Now it can be, intelligence is, say, log of shoe size or square root of shoe size. Those are not linear models. It is possible to capture them to some extent using traditional models, but machine learning explores a vast area of non-linear models. Linear models are a special case of non-linear models, where a non-linear term is set to 0. And hence, we can explore a vast, bigger set of models, and that's why the prediction power is such more powerful. Again, one of the sort of bedrocks on which traditional models have been built on is you assume a statistical distribution. All statisticians are very familiar with this. You use a Gaussian or distributions from the exponential family, but there are a very, very solid theory between why you assume a certain distribution. And all those distributions have certain nice mathematical properties that let you fit the models. But real life data will not come from any textbook mathematical distribution. It never happens. So people make approximations and then they try to fit the model, hoping those assumptions, approximations are not too bad. But if I even take away that tenet, that I take away even assuming any statistical distribution, then I'm not limited by the amount of mathematical power within the statistical distributions. So I can explore a vast, bigger series of models like that other one. Another issue with traditional statistical or traditional tools is if you have extreme values in the data. We call them outliers. So what it essentially means is, suppose you have a bunch of claims, a few of them are very big, really, really big. They probably go to the reinsurer. What a traditional practitioner would do, he would take out those claims from the analysis, run the analysis on a separate claim, like the smaller claims, non-extreme claims, and then do something special for those outlier values. If you don't do that, then your model will get horribly wrong. And how can that happen is, when you're fitting a traditional model, the model does not really know how much importance to give to each claim. It treats every data point as equally important. So, if it fits a model which is bad on those high extreme values, it will try to adjust itself so that the prediction of those extreme values is better. And in trying to do so, it will mispredict the rest of the data set. So you don't really want to do that. That's why people like separate them out and do separate analysis. But again, in machine learning, it can really, without doing all these sort of handcrafted solutions, you can do all of them, you can push in all the data, and you can fit a model which will not fail and will not try to adjust itself just because of a few data points. It will take care of them appropriately. There are lots of tools to do that. So that's a bit of like practitioners sort of, it helps a real practitioner to really see what is actually going on in the model without trying to do handcrafted solutions. Another important fact is, well, if you put in, say, you put in 20,000 variables and you're trying to predict something, and you really do not know which of those 20,000 variables are predictive, has actually information content to predict. What machine learning will tell you, out of those 20,000 variables, which one is it actually using to make the prediction. So it tells you which are the irrelevant predictions. Now, if you say, well, I cannot collect tons and tons of data. Well, if you have 20,000 data points about a particular risk, you feed them in, machine learning tells you, well, out of these 20,000, maybe 70 of these, say columns 1, 23, 27, 70 of these are important. Then what you can do is, go ahead and collect more information about those 70 variables to improve your prediction power. You do not need to go on collecting information and storage costs increase from all those 20,000 variables. That's what machine learning allows you to do. But some statisticians might say, well, you can also do that in traditional statistical methods. You can do them, but they are very limited. And the way machine learning does them very efficiently and fast is without performing any statistical tests. And that you can do that because it does not assume any statistical distribution. This is the one property of like a class of machine learning algorithms. Not all algorithms have this property, but this is a very, very well-known property. I'll go on to a few more advantages. This is a common issue in real-life data sets. You have incomplete or missing data. Again, what practitioners generally do, well, if some variable fields are missing, traditional method, if you do not do any sort of engineering on those missing fields, traditional method will simply ignore those rows, ignore those data points altogether, because they need complete information to make a prediction. What machine learning can do is elegantly handle them. Now, a common technique used by people, if you have missing data, is to impute them. It's called imputation. So they look at the adjoining fields, the neighboring fields, and maybe take an average value and put that average value in the missing area. Machine learning lets you, without going through those assumptions, you can still go ahead and make the prediction. So any values, missing values, incomplete values, you can elegantly handle them without the practitioner needing to make any specific assumptions on how to fill in those values. So even with imperfect data, you can apply machine learning. Well, Henry talked about this a little bit. These methods are highly scalable. So yes, it works not just on big data, it can work on small data, but it can also work on tons of data. And the speed compared to traditional methods is amazing. Well, it can take like 2 weeks to train a model sometimes, but if you go in the traditional domain, you will never be able to train such models. So they are highly scalable. I talked about this before, so it does not really have to be a big data set, even small data sets. So like for like, a machine learning algorithm is very, very likely to outperform a traditional method of approaching the same problem by a very large degree. And I think Jason is going to give you a sort of a demonstration of that in his presentation. We talk about machine learning. So here is something what you can call about the learning bit. So if you feed in more data, the machine does not, or rather the algorithm does not ignore its past training. It slowly adapts and changes its training, changes its prediction depending on the new data set. So if you have a stream of new data coming in and there's been something changing, and in a traditional sense, you will have to refit your model. In a machine learning model, what you can do, it can slowly adapt to that changing regime. So if you think something really is changing, you can let the machine run, pour in the new data, and the machine will slowly adjust itself because it's trying to make its prediction as accurate as possible. Something close to online learning. Okay, I'm going to talk about one specific use case, and I'll list a few other use cases. So risk selection and pricing is very important for insurers, as well as a sort of like solid workaround for actuaries. So quickly I'm going to jump to this. So one of the use cases is people use GLMs a lot. So products, especially in personal lines, and short description is if you use machine learning algorithms in the same context, same data, you can use them to improve your model. If you don't want to replace your model, you can definitely use it to improve your model's predictive power. Another scenario is Monte Carlo simulations. If you're pricing a very high layer in your insurance, you would probably run thousands and thousands of simulations to see how many times I'm hitting that layer, how much am I hitting, and then sort of it helps you to arrive at the cost. So that's called Monte Carlo simulations. Again, machine learning can be used to make those simulations much more informative, so you do not probably have to run so many simulations, or the design of the simulations can be much more informative. I'm going to skip on, and okay. So going on this topic, so as I said, particularly for GLMs, because this has been the bedrock of modeling for a long, long time. This is very well grounded statistical theory. So there's lots of other issues. I just summarized a few issues. And how can machine learning help? Well, we're not suggesting you totally throw away GLMs, but there are a lot of techniques. I've named some of them as given random forest. These are the fancy terms. These are not subject to these limitations, and there are other limitations with GLMs. So they can be scalable, they are highly predictive, they can handle incomplete data sets, they can handle large, small data sets, and yes, they can be biased, as I explained, but generally the case is that if you use some of these techniques, and they are all available for free, let me stress that, then it's very, very likely that your prediction is much more accurate than the traditional techniques of GLMs. Some of the other use cases, I'm going to briefly run through this. So customer retention modeling and customer churn modeling. A lot of people have used machine learning. I'm not so sure about how much in the insurance industry, but banks and other people have been using machine learning to predict which customer will renew with us, or customer loyalty, if you like. Claims and fraud detection. An example was given by Henry, and this has been used in banking for a long time. Okay, maybe not a long time, but this has been heavily used in banking. Cross-selling, so you need to predict which customer can I upsell or cross-sell to. Again, that's a prediction problem, and any prediction problem, you can use machine learning. Another use case is market segmentation. So this is not really trying to predict, it's trying to find out important groupings within the market that you're trying to target. And maybe you can customize your product offering depending on the group or the characteristics of the group. So market segmentation comes under the branch of unsupervised machine learning. And this is obviously like quite important to people. You want to target your advertisements, or you want to target your products depending on which market segment you're trying to target. Strategy optimization. A lot of people use capital models to do reinsurance optimization. Strategy optimization is one of the holy grails of machine learning, as Henry mentioned. The game of Go, in which DeepMind beat the world in the world number 2. That's like playing a game. It's like trying to optimize the strategy and come up with the best possible strategy to beat your opponent. In this case, the opponent is the external world. So you're trying to make the best reinsurance purchase or optimize the reinsurance program in such a way that you minimize your reinsurance premium paid out, or some of the metric like ROI, or whatever you're trying to predict. So it's a strategy you need to find out, and machine learning can definitely help because it's the same problem in a different context as playing a game of chess or a game of Go. Okay, it's probably my last couple of slides. So I've talked a lot about why now and what is this and how can machine learning help. So well, how do I get started? First of all, you have to identify the business problem. It can be any one of those use cases, or it can be another case that you can think of, in which either you have to optimize something, some resource, or you have a prediction problem. You want to predict something. So machine learning can definitely help in any one of those cases. You identify your business problem, you identify the relevant data, and this can be internal data, it can be external data, and public data also. So gov.uk is our website in which the UK government has released a lot of public data sets, so you can use that. Then you have to choose a modeling platform. There's a debate between which platform should I use. I'm going to give you some examples. The first one is Amazon Machine Learning, the second one is Windows Azure. These two are commercial software, you have to pay for them. However, both of them offer you virtual computers in the cloud in which an environment is set up for you to go ahead and do machine learning. So if you choose that sort of setup, all you pay is for the hardware cost. How much CPUs you're using, how much memory you're using. Or you can buy the off-the-shelf products, which are plain vanilla products, not specially bespoke made for any particular industry. Or you can use, these are two examples, there are many more examples of open source tools. You can go on the internet, download R is a programming language. It has lots of machine learning libraries. H2.ai is a company which builds machine learning algorithms and distributes them for free. So you can go on the internet, download them, you probably have to sign up to a newsletter or something like that, and that's it. And you get daily, monthly or quarterly updates to the algorithms. As and when new algorithms are introduced, it will be included in both of these packages. So after you choose a modeling platform, depending on what you choose, you try to build a prototype model, and then you test the performance of the model and fine-tune it. And by fine-tuning, I mean try to change your model parameters, model structure, try various algorithms to find what best suits your problem and what results in a best prediction. And then you deploy the model. So once you deploy the model, you have to continue monitoring the performance of the model. So if your data changes, if there's an underlying change in the business problem, obviously you have to monitor performance and see, well, is the model still suited, or do I build a better model? Or maybe there's a new algorithm that's come up, which is much better at making this sort of prediction in this sort of context. So yes, you deploy the model. This is a brief snapshot of how a machine learning pipeline works. So you select the data, you model the data, then you validate the model test the model, use the model, tune the model. So I'm just quickly running through this. So this is sort of a pipeline what you would go through if you choose a problem and then start building a machine learning